Hello again, folks, in 113. Today we're going to be covering section 11.3, which is known as expected value. Right? Here again is that sort of overview where this is where we have been, this is where we are, and this is where eventually we're going. Let's just verify with the calendar here. Okay, Thanksgiving has passed. Today is the last day of November, Tuesday, November 30th. So we're covering 11.3. Very good. There's just 3 more sections there for this one. The packet consists of the following. Here's a very useful, I hope, overview diagram of this concept, expected value. There's basically 2 formulas that you will need for this section. The actual expected value formula, which involves probability, and then something known as fair price. Okay, so we're going to go through that. What I included was snippets of the same material, the same information, if you prefer, from the textbook. Maybe you feel better than my explanation. You have that at least. And then just the actual examples. There's 7 of these, so we'll go through that. Okay. Very good. So if you're going to follow along, print this out and maybe annotate as we discuss. We, the royal we. And let me fire this up and adjust the lights as always. Okay. Definitely have to move that. Okay. That is way off kilter. Here we go. Much better. Let's see if I can get this to make it easier to see. Okay. That looks like it's visible. Very good. All right. Again, here's the rundown. We had been discussing Chapter 11 the last 2 classes just before Thanksgiving, in which case we discussed Intro to Probability and then compared and contrasted probability to something known as odds, which is very similar sounding and related certainly, but not exactly the same thing. All right. Today we're going to be covering expected value. So, with that in mind, I'm going to erase this. And we'll get busy. It's not that sunny. I'm a little worried that my board may need to be adjusted. See if I aim that a little bit differently. Okay, that looks better. Okay. Okay, here's the overview diagram. Humor me as I discuss the intricacies of this. Alright. Is that legible? I may need to adjust the lights a little bit more, so my map here. I think that's a little bit better. Okay. Alright, expectation is the main concept today. Right? An expectation is to articulate an attempt at translating theoretically opposing outcomes. Alright? Benefits and losses. These are things that are regarded as being negative or positive. Alright? Translating them into a net sum, right, which is why you see this symbol here, the Greek sigma. Often used to imply that things are added. Right? For the sake of deciding how to proceed, what is in your best interest in the long run. Right? It's a strategy basically of applying probability to unique circumstances to decide whether it's to your benefit or not to bother. Right? In the long run is the key phrase. This is done by factoring in respective probabilities. The probability of benefits and the probability of losses. These are opposing outcomes. All right, now this is the general formula, if you will. All right, sigma, and then in parentheses, probability times an amount, if you will. All right. Now, each P is the probability related to each A, all right, which is if it's about money, a lot of times, is the individual dollar amount, right, which you'll have to translate. It isn't explicitly stated what is negative and what is positive, all right. If the outcome, the sum, remember, when you see sigma, Greek sigma, it is implying that you're going to add somehow. Now you know that it's a combination of signs that dictates whether you really add or subtract, but in general, all right? If the outcome is a negative, you would consider this a disadvantage, all right, in the long run, right? If the outcome turns out, the sum turns out to be a positive, then you would consider it an advantage. So you play the game or whatever is involved. Right. If you get 0, it means you break even, which means that it's a fair game. Right? And you neither lost nor you gain anything. Right? Just had the experience, which is kind of a gain in itself. Okay? So if you see sigma and then in parentheses these two ideas, a probability and essentially an amount, that means that you can have an infinite number of terms. Whatever the circumstances require. All right, so something plus something plus something plus something plus something into infinity. All right, that's just a generalization. All right. This is essentially what it looks like. All right. Take this as a model. All right. When you're trying to do any of this work in my lab or work problems in general, take this model and try to fit the unique description, the unique circumstances as they're described, into the model. Right? These ellipses indicate that there are more terms here if they are necessary. Right? You'll probably at minimum need a benefit term, if you will. These two things multiplied, the probability and the amount that would be to your benefit, plus a loss term, if you will, at least one, of, again, a probability of losing and an amount associated with that. Okay. This is basically an expansion of the generalization. Right? So to see E equals these terms in succession like this is an alternative way of writing this. The expected value, the sum of expected value. Right? Or you could write it like this. The sum of probability times the amount related. Okay. When it comes time to discuss this, will be the last couple of questions in the section pertaining to fair price. Let me just touch upon it right now. Fair price is the amount one should actually pay, all right, in order to break even in a fair game situation. All right. The practical way of writing it is like you see here, the expected value as it is given to you or that you calculate, all right, plus whatever the actual cost of like playing a game or something, $2, whatever, a raffle ticket perhaps. If you combine these things, that would determine what the fair price ought to be, all right, never mind what it is. All right. And you could rearrange this if you need to figure out either of the other two terms here, expected value technically or the cost to play. Let me just make sure that we're clear about something, this in particular. Breaking even, all right, what is breaking even in terms of a monetary value? $0. All right. All right, so the expected value would be neither a gain nor a loss. Okay? All right, now let's do some examples and I'll try to obscure whatever is necessary. And here are the actual examples here. I'll give it the view here, the thumbnails. Okay. See if my red holds up today. Hopefully we'll forward some new markers if necessary. Okay, assuming you can't really read this from far away, let me go through the process of rephrasing this into its as a sort of an exercise in and of itself. All right. JetBlue Airlines is considering adding a route from Boston to Minneapolis. Before making a decision, the company needs to consider many factors, including potential profit, which you would regard as a gain, a benefit, or loss, which would be a negative, right? A disadvantage. After considerable research, JetBlue estimates that if it adds the route, this particular one, there is a 60% chance of making an annual $800,000 profit. Simultaneously, a 10% chance of breaking even, and a 30% chance of losing $1 million. Right? How much can JetBlue expect to make annually on this new route, and without it being added in the long run? Right? So, for the sake of deciding whether it would be your advantage or disadvantage, we're going to basically borrow this formula. E is equal to a percentage, a probability, essentially, times an amount associated with that, and then if necessary a second one, and if necessary a third one, a third term, right, of probabilities and related amounts, if you will. Okay, it's a little faint. Let's see if this makes it a little bit easier to see. I don't know if that's better or worse. All right. And now to rephrase this, essentially an airline must consider the potential losses or benefits. All right. So notice that what I did is I read this, I circled the numbers involved. Again, that's always a good strategy when you're trying to decipher a word problem. All right. The numbers involved, and if I were really a good guy, I would have maybe color-coded it. All right. Let's try this first term here. All right. And just to stick with the model, let's call this the advantage or the profit benefit term. Okay. Benefit. Call this break-even amount. So the break-even term, if you will, and a loss. Okay. The probability is given in the style of a percentage for the benefit. If they add the route, it's 60% chance of making an annual $800,000 profit. So one would assume that a profit is indeed a benefit. So I'm going to put 60% in the style of either a fraction or a decimal. Right, remember, your percentages are really your probabilities, which means that you could use them either as a decimal or a fraction in the actual calculation. So if it's 60%, it's 0.6, right, in this first term here. And the amount of money involved would be, although I'm squeaking it in here, $800,000. Right. In the second term, the break-even term, it says that there's a 10% chance of break-even. So 10% in the style of a percentage would be, a probability in the style of a decimal would be 0.1. Right? And if it's breaking even, although they didn't explicitly write $0, one would have to assume that that's what it is, 0. And then finally, the loss term, a 30% chance of losing $1 million. Right? So 0.3 for 30%, and then 1 million to squeak it in here. And we have everything filled in that we need. All right. Now, you might look at this and immediately go, oh yeah, if you just had to speculate, Is this to my advantage or to my benefit? You might seeing this as a larger loss of $1 million, go, oh yeah, absolutely bad idea. All right? Don't get involved in this in the long run. But you have to bear in mind that there are probabilities involved here. And the probability of a loss is actually less, apparently, it's 30%, versus the probability of the benefit, which is greater, 60%. So you'll see overall, it's sort of an average, if you will, all right, whether it is in fact a benefit or a loss. All right? If you multiply, and you could use a calculator if you like, all right, 0.6 times 800,000, you would have something like this, right? And you see that it is 480,000 for the expected benefit portion of the show here. Get rid of the gobbledygook. So the benefit is potentially $480,000 overall. The break even, you don't need a calculator because it's 0 times whatever the percentage is. So this basically is excluded entirely. You don't even have to worry about it. And then 0.3 times a million would be 300,000 reasonably, right? So it ends up being minus because it is in fact a loss. So there's a couple of ways, like I know that there's we use pluses or minuses in the formula. If you've decided that this is a loss, you have to remind yourself to translate this into subtraction. Okay? And then put the dollar value. So 300,000 is what you would end up having to subtract. Right? So what would end up being the expected value here would be the difference of basically these two terms, because breaking even is just 0. All right? 480,000 minus 300,000 would be what? 180, right? What is the sign of this overall? All right? As a result of doing this subtraction, it would be a positive. All right? So if you end up with a positive value, whatever it is, even if it's minuscule, all right, it would technically be an advantage in the long run. Barring some other considerations or some faulty research. It's an advantage. One would have to assume that. Right? It's kind of cool, right? It's basically applying math to give you a number so that you get a feel for whether you've made a good decision or a bad decision, or that it would be a good decision or would be a bad decision. Right? Using probabilities. It's kind of cool, right? All right. So what you expected value would be a profit in the long run. Now, as a student, you might be more interested in something that is less monetary and more practical, which is something like example 2 here. All right, a test-taking strategy. Let me clean this up a little bit. This will give you a real feel, because it's maybe more immediately to your benefit to think about, and not just about, say, market research. Here's the formula again. I'm going to write it in green. And we could modify it as necessary. You may not end up needing this many terms, but there's the model to fill in. All right? Maria is taking a multiple choice exam in which there are 5 possible answers. That's important. Right? It's multiple choice. There are 5 possible answers, right, to each question. Right? The instructions indicate that she'll be awarded 2 points for each correct, and she'll lose a half a point for each incorrect. and that no points would naturally be added or subtracted for answers left blank. So no points, 0, for those left blank. Right? Now, first part is, if Maria does not know the correct answer to a question, is it to her advantage or disadvantage to guess at an individual answer, or to guess at an answer? I'm adding words that aren't here. Right. Let's take some time to figure out what the probability would be per answer in theory. Right? Notice that in this problem, you're not given percentages. No percents given. So that means that you have to determine the probability yourself. Right? And that's not hard. Right? In this case, it might be more intuitive to consider probability not so much as a percentage, but as a fraction. Right? So let's say that you were going to calculate the probability, and I'll put this in blue, that a person guesses correct. So in the shorthand notation of probability, I'm writing it in this sort of quasi-function style here. P of, and then you read the contents of a parentheses. Guessing correct. What would that be? For each individual question, if there are 5 possible choices for a multiple choice, how many are going to logically be correct? All right. 1 out of 5 would stand to reason, right? Now, simultaneously, we're going to need to figure out this additional probability, the probability of not correct. Well, it would be the balance that adds up to a maximum of 5, right? So if it's multiple choice again, and there's 5 choices, and only one of them is correct, how many are not correct? It would probably be more likely that a person guesses incorrectly, right? So it would be 4 out of 5. Okay. So let's take these fractions. You could make them a percentage of 0.2 for 20% and 0.8 for 80% if you like. All right, that's what the equivalent would be, right? This is 1 out of 5, so that's 20%. And this is 4 out of 5, so that's 80%. If it makes it feel more intuitive. But using a fraction is totally fine as well. So I'm going to squeak them in here in the model. All right, let's call this the benefit term. And we'll call this the loss term. And we'll use these appropriate probabilities here for the p-values. Right? So the probability in this case would be 1 out of 5, or 0.2 if you prefer. And the probability in the loss term would be 4 out of 5, or 0.8 if you like. I think people probably gravitate towards decimals because they have a calculator on hand, and there's no sin in that. All right. What are the point values that are associated with? Well, if a person guesses correctly, you're awarded 2 points for each correct. So you would say that this is the probability times the benefit of positive 2. You know, you don't have to put the positive if you don't like. And for the loss, it would be only losing half a point. So it would be times a half, or you could say 0.5 if you prefer the decimal. If you end up with fractions of something that end up being irrational, pardon me, not irrational, but repeating decimals, like 1/3 would be 0.333 forever and ever and ever, it would be to your benefit in that instance to use the actual fraction. Right? But for terminating decimals like a half, that's fine. 0.5 is legit. All right, now do remember again, if this is a loss, one has to intuitively translate this to a minus rather than a plus instead. Okay, for the loss term. Right? They did mention the other thing, all right, that no points would be added or subtracted for answers left blank. All right? The probability is not even under consideration in that case. All right? So, and it would be 0 for the amount of points added anyhow. All right, so you really don't have to consider this middle term and just think about the benefits and the losses exclusively. All right, now I'm a little short on space, so what I think I'll do is maybe erase what I have here and then put the results down here. So, if it is 0.2 times 2, it would logically be 0.4 if you've done it in the style of a decimal. If you did it in the style of a fraction, remember you could just stick a 1 underneath the value of 2, and then do top times top, which would be 1 times 2, and bottom times bottom, which would be 5 times 1, which would be 2/5. Right? 2/5 or 0.4 as a decimal, right? Either is fine, all right? We've decided that this is a negative because the second term that is relevant here, because it is in fact a loss, all right? Again, if you did 0.8 times 0.5, what would you get? It would be 0.4 again, wouldn't it? Yes, it would in fact be 0.4 again. All right. If you translated it into fraction form again, it'd be top times top, bottom times bottom, which would be 4 times 1 and 5 times 2. That would be a 4 on top and a 10 on the bottom. And although I don't want you to have to reinvent the wheel, and you could in fact use your calculator, remember that if you are going to add or subtract fractions, if you did it this way, then you need to upgrade the denominator from 5 to a common denominator. It would be appropriate to translate this into so many tenths, is what I'm saying. So 5/10 is, 5 translated into tenths would be times 2, and you notice, wow, that's a remarkably similar figure. All right, it's identical. It would be 4/10 minus 4/10. All right, so what's 4 minus 4? It would be 0. All right, 0/10 overall, or you could just simply say 0 decimal point. All right, so if that is net, all right, and net is just implying that you've added or subtracted the sum of the parts. All right. Then this strategy doesn't really amount to a benefit or a loss in the long run. Right? So this is break even, essentially, situation. It is neither a profit nor a loss. Neither a benefit nor a loss. Black is starting to die here. Okay, this is to part A. Alright, if Maria does not know the correct answer correctly, is it to her advantage or disadvantage? Just to reiterate, come on. It's neither a benefit nor a loss. Alright, that's the way that the sum would work out. Then you notice in part B here, the conditions are changed very slightly. So let me free up some space. And we'll modify this further still. Okay. All right. If she can eliminate one of the possible choices, meaning that there's just going to be 4 multiple choice options. Is it at that point to her advantage or disadvantage? To guess. The points have not changed. It's still 2 points for correct, a half for a loss. All right, here's the model again. And we already know from experience of dealing with it that we're going to need just two terms here. So I'm going to shorten it without including the middle term. It's not really necessary. All right. What would be the probability of guessing correct in this instance? Well, instead of it being out of 5, right, there's only one correct answer. Instead, out of 4. All right. And instead of probability of incorrect, again, being 4 out of 5, it would be 3 out of 4. All right, so we're going to just situate them in each of their respective terms. So 1/4 for the probability here, or if you like 0.25, and 3/4 if you like a fraction, or 0.75. Right? The potential points is 2 still, right? And the potential loss would be 0.5 point. And again, we have to intuit that this is going to subtract because this is a loss term. And this is a benefit term. Okay? So, if you follow the intricate work here, right, you'd end up with 2 out of 4. One times 2, 2 out of 4 for the profit minus 3 out of 8 for the loss. All right, and then upgrade to a common denominator of 8. So 4 times 2 is so many eighths. All right, and therefore 2 times 2 would be 4/8, of course. Now you could subtract legally speaking, right? Unless you're using your calculator, is fine. All right, 4 minus 3 would be 1/8. All right. So since this works out to be a positive overall, this would be a benefit in the long run. Okay. You might potentially, you could think about it as, even whether it's true or not individually, you could think of it as being a sort of positive 1/8 each time you guess. All right, or that, in this case, Maria guesses, right? Okay. All right, let's take a look at 3. For example 3, it says expected attendance. For an outdoor concert, event organizers estimate 20,000 people will attend. 20,000 people if it is not raining. And a significantly smaller portion, 12,000 people will attend an event if it is raining. On the day of the concert, meteorologists predict that there is a 30% chance of rain. So I'll put that in red, just the color coded. And they don't give you the balancing of information. One can infer that. Determine the expected number of people who will attend this concert. Right? Here again is the generalization. The expected value would be probability times an amount plus probability times an amount associated. The subscripts, I should elaborate, all right, are just a label, right? If you see a superscript, that is, it's a smaller font a little bit higher up than either of these two letters, that is an operation of exponents, which you don't have to worry about. Okay, so there's a 30% chance of rain. We have to sort of, unfortunately, rephrase this just a little bit. I'm going to start with this, right? Based upon the way that this was written. They say the probability essentially of rain is 30%. Right? We could say 3/10. One could infer then that the probability of it not raining would be the balance, right? Remember, probabilities are a maximum of 100%. So if it's what's the balance out of 100? Right? It would have to be logically 70%, right? Or 7/10. Okay. So you don't have to put the benefit term first. I just have a tendency to do that myself. And the loss term second, but we'll go ahead and do that, right? So squeak it in this information. I'm going to use black just because I think it shows up when I overwrite up here a little bit because of the lighting situation. All right. If we consider the benefit, and the benefit would be 20,000 people in this instance, right? The probability in that event would be 0.7 times 20,000. Right. If we look at the loss term now, the probability would be the only probability that is quoted here, which is 30%, so 0.3. And the amount of people in that event would be just 12,000. Now this is an interesting case because is there any real negative in this case? Right? People are coming no matter what, right? A significantly less portion, granted, but if you're having an event, you're probably ahead of the game already, I guess. There's no real negative in this case. Right? It's not like you're going to have negative people, right? Event goers, people in attendance. It's just a smaller percentage of people. So it's not going to be 20,000. That will be the maximum essentially, but we'll see what it calculates out to be. All right. So if you have 0.7 times 20,000, what that ends up being is should be 14,000. If you have a possibility of rain, people are still coming. 0.3 times 12 would be 3,600. And then again, because you're still having people come, you're not getting a negative value of people. There's no such thing as a negative person, right? Not really, huh? Maybe they have a bad attitude, but they're still present is the point. So you're gonna just leave this as a plus, right? And then add them. What would it be? 17,600 people. Right, in the long run, all right, and it's a positive. All right, it's not going to be the maximum. All right, it'll be something smaller than that. All right, but it's still you still have people in attendance. People are coming no matter what. It's just less than the maximum. Okay. All right. Okay. Skipping one, sorry here. A door prize. Okay. Power's too tight today. Example 4 is about a door prize. When Josh attends a charity event, he is given a free ticket for $50 for the $50 door prize. Right. A total of 100 tickets will be given out. He has a free ticket, and it's $50 is the actual prize. All right. Determine his expectation of winning the door prize. So, again, here is the formula to generalize. We would at minimum need a benefit term and a loss term. Okay. Now a couple of things. This is sadly purposely vague as just to get you to think a little bit deeply independently. So it's a mental exercise of inferring what isn't explicitly stated. Firstly, we're going to need probabilities, right? But they're not stated, so we'll calculate them. And again, if this is the benefit term, I'll use that blue. And if this is a loss term, I'll make that red. Right? What is the probability of winning this raffle? And I know that they didn't say the word raffle, but one would have to figure that it is, right? Why? Because there's a ticket involved here, and there's 100 tickets. So that means that, unlike the lottery, a raffle is a guaranteed winner, somebody, not necessarily Josh, but, you know, what's the probability of winning a raffle if you have a free ticket? Right? It would be the number of tickets out of the total given tickets. Right, so if this person got a free ticket, that's 1. And if the total is that there's 100 tickets, then it's 1 out of 100 is the probability, or 1% probability. Right? Whoever the person. Right? What would be the probability of losing the raffle? It would be, as it is always with probabilities, the balance. Right? So if there's 100, right? If there's only one chance in 100 that you're winning, how many chances in 100 are losing? A lot more, right? So it would be 99 out of 100. Okay? So I could fill out that information up here. 1 out of 100, or you could say 0.01. And 99 out of 100, you could say 0.99. Okay. Now, what does the person stand to gain in terms of an amount? This takes a little bit of thinking, right? What's the total prize? It would be $50, right? But normally minus the cost of the ticket. The question in this case is, did the person actually pay for it though? Right? The cost is actually $0 because it was a free ticket in this particular case. So overall, it's just going to be $50 is the benefit here, benefit amount. So I'm going to put a slip of 50 in place of this first A. All right. Then on the losing side, the amount associated with that, it would normally be the cost of the ticket. But again, in this unique situation, the person got a ticket for free. They didn't pay for anything. Right? So it's actually $0 because it was free. Right? Which means that a 0 would go up here. Now, without doing too much math, all right, is this going to be a disadvantage at all? Not really, right? Because if the person didn't pay for anything, then they haven't taken a hit in any way, shape, or form, right? What they're gaining, even if they don't win the prize, right? Even if they don't actually win, is the experience. That's kind of the hidden benefit or loss, right? The experience involved, right? You played a game for no money, right? So you're already ahead technically, right? The question is how much, right? 0 times 99 out of 100, regardless, is going to be 0, so you could cancel that out entirely, that term. What you're going to figure out exclusively in terms of benefits would be the equivalent of 50 times 1 out of 100. So the decimal equivalent is probably a little bit easier or intuitive, right? Actually, not necessarily. If you made this a fraction, right? 1 out of 100 times 50 over 1, you could simplify before you multiply, of course. Right? The common factor, the GCF of 50 and 100, one thing above the line, one thing below the line, is simplifiable before you multiply, is 50 itself, right? So it ends up being a fraction of 1/2. In terms of money, though, right, what's a half? 0.5. So you could write it in the style of money, 0.50, 50 cents. Person did not lose anything, but in theory they've gained 50 cents worth of experience, if you will. All right, even if they don't win the prize. That's his expected value. All right. It's not quite $1, right? Because the chances of the person winning are quite slim. It's 1 in 100. All right. But given a free ticket, it's still to a person's benefit to play. You can think about it as you've won an experience. All right. Now, if you look at 4, the conditions change ever so slightly, which makes it interesting. Okay. Let me clear up the gobbledygook. When Josh attends a charity event, he is given the opportunity, yay, the opportunity, right, to purchase a ticket, right? You could buy one, good for you, instead of having it handed to you, right? It's still a raffle if it's a ticket, right? It doesn't involve any lottery numbers. To purchase a ticket for a $50 door prize, it's almost the same situation. It's still $50 as the prize, but in this case, it's going to be purchased. Right. The cost of a ticket is $2, and there are again 100 tickets to be sold. Determine Josh's expectation if he purchases 1 ticket. Okay, now let's, again, if this is the formula to generalize, P1A1 plus P2A2, and this is essentially the benefit term, and this is the loss term. Incidentally, if it seems a little redundant to write something over and over again, don't ever feel bad, especially in the position of instructor, right? Repeating yourself helps people remember. All right? It helps you learn, it helps them learn. Okay? In this case, let's consider the probability of the benefit here, term. All right? The conditions, the probability of winning, if you like to put the word of to remind you, that's how you read parentheses, is of and then what are the contents of it. It's still 100 tickets. The person is still purchasing 1. So the chances of winning are, if it's a raffle, 1 out of 100 still. Right. The probability of losing is still 99 out of 100. That much hasn't changed. Right? But because the person is presumably purchasing a ticket this time, one ticket, all right, we have to factor that in when we're considering the benefits. So, all right, the benefit, the A amount, all right, would be in this case the prize amount of 50 minus the actual cost to the person. So if it's one ticket, it's going to be $2 less than that. So that means that overall, this is really $48. All right. I'll fill in some information. It's still 1 out of 100, but now times 48 as the amount associated with that probability. Okay. Losing, all right. The amount associated with losing is just basically the cost here, right? In the last problem that is similar to this one, it didn't actually cost the person, so we used 0, right? But in this case, he has to actually pay for it because he has the opportunity, right? So that's $2, right? Not a heck of a lot. And that's that. So I moved my board, so I was like, sorry. Let's factor in 99 out of 100 again, times the dollar amount, $2. Right. Now in this case, because we're dealing with an actual value, and the person is going to potentially lose that amount of money, a negative amount of money, in this instance we have to figure that this is in fact subtraction. Okay? So let's calculate and proceed. All right. I'm going to do it fraction style in this case. 1 times 48 is 48. 100 times 1 is 100. And that's a positive. All right. This is 99 times 2 technically. So minus 198. 1 times 100 is 100. You could do the decimals if you like. All right. At this point, if it's out of 100, you can think about this in terms of dollars and cents, right? 48 out of 100 is 0.48 cents, right? 48 cents. Right? 198, it's an improper fraction, granted, right? But it's still out of 100, so you can think about it still in terms of money, all right? Without actually doing the division, which essentially is just accomplishing that, all right? The negative dollar value in this instance would be $1.98. All right. Now, if you subtract these, all right, because you have a larger magnitude that is essentially negative in this case, you're going to have a disadvantage if you play the game now. So, what does it end up being net? Negative $1.58 it should be, right? $1.50 rather. So this is a loss in this case. All right. Think about it this way, though. All right. The cost of the ticket was $2. All right. All right. Did you lose $2? I'm sorry, Josh, not you. Did Josh lose $2 though? No, the portion of this, you can kind of think about this in a nice way. All right, he paid 50 cents, right? All right, he gained 50 cents worth of experience. You know, yes, he lost $1.50, but he also he got an experience out of it. You know, so it isn't entirely as bad as it could be, at least. I'm trying to be an optimist here. You know. So it's the expected value would be negative $1.50. Yeah, I wouldn't bother in a case like this. Josh shouldn't either, but you know, just realize that it's not quite $2. You know, so even if that's what it cost, you did get something out of it. Apparently the experience was worth 50 cents, right? Okay. one more of these type, and then we're going to shift gears and talk about fair price. All right, here we go. They finally decided to call it Raffle Tickets. And we have a different participant here. Irene! Here again is the general formula, again, intentionally repetitive for the sake of helping a person remember. Right? If you need extra terms, you're welcome to include that. Right? Now, here's a situation of a raffle, but there's a greater number of tickets. 1,000 raffle tickets are sold for $1 each. Right? 1,000. And they're $1 each. Right? One grand prize is $500, right? And 2 consolation prizes of $100 would be awarded. Right? The tickets are placed in a bin, as raffles are, all right? And the winning ticket will be selected from the bin. All right? Now, the winning tickets will be selected from the bin, assuming that the probability that any given ticket selected for the grand prize is 1,000, 1 in 1,000, and the probability that any given ticket selected for the consolation prize is 2 out of 1,000. Determine this participant Irene's expectation if she purchased just 1 ticket. Right? They're giving us the probabilities. Right? Notice the fraction here and here. Right? But in this case, we have 2 scenarios. We have a grand prize and we have a consolation prize, right? So we're going to have to tweak this a little bit. In this instance, right, you could kind of, since there is this consolation prize, there's really 2 benefit terms here. There's a first benefit, a grand benefit, if you will, and then a consolation benefit. But there's going to be losses as well, all right? So I'm going to have to add another term here. I need a third PA term, call it P3A3, and this will be the loss term overall. Okay, let's figure out the just translate what is basically stated here. The probability that they have described of winning the grand prize, all right, is 1 in 1,000. You might be, if you're like me, a little anal, and you're thinking to yourself, like, well, did they put the tickets back or not? Don't even worry about it, because they're not. We're not there yet. That something, a condition like that is forthcoming in section 11.5 or 11.6. All right, we're just going to stick with the information that they've given us and not think about it more complicated than that. All right, grand prize win is 1 in 1,000. The probability of a consolation win is 2 in 1,000, because there's 2 consolation prizes drawn. All right. What is the amount, though, associated with winning a grand prize? The grand win would be the total that it is, which is $500. But you have to factor in that there's going to be a cost here, right? If the tickets are not just given, as in the case of Josh, example 3, I think it was. What was it, example 4, whatever. The first problem involving Josh, where he was just given something. If the person is purchasing 1 ticket, how many is each ticket? $1. So we'd have to figure out that, yeah, the person is going to have a net amount of money that's greater than the cost of the ticket, right? But it depends on how many that they're buying here. So if it's $500 that the person in theory would win, factor in that they spent $1, so it would be $499 technically, right? All right. what is the consolation win? Right. That amount. Each one of those prizes is 100, right? So figuring out the first example, it would be $100 minus the cost of however many tickets there are, right? It's still one, same ticket, so that would be $99. All right, let's start to fill in the model here. Probability 1 in 1,000, and the amount associated with that would be $499 in theory. So we would have these multiplied. I put these parentheses here as a reminder to you that you really should do the multiplication before you add or subtract, as in all order of operations type of problems. We're not performing algebra here, we're just sticking with the right side of the formula. So arithmetic. The second probability, still a benefit, would be 2 in 1,000, because they draw twice in theory. But the odds are, the sum is not as great. So $99. Still positive. All right, that's good and legible. All right, now the loss is the amount that we're going to subtract out of this in theory. All right, but we have to figure this out. Okay. What is the probability of losing? Entirely. All right. Well, the probability of winning is 1 in 1,000. Like if I were going to generalize these two, right? If I'm going to discuss not individual examples, but in general, the probability of winning entirely, right, would be 1 in 1,000 and then 2 in 1,000, which would be 3 in 1,000. So the probability of losing entirely, not specifically, more of a generalization than specifics are these two things, would be the balance out of 3 out of 1,000. So what would be the balance? Remember, they always add up to a maximum, in this case of 1,000. So what's 1,000 minus 3? 997 out of 1,000. All right. What is the amount associated with losing? If you lost entirely, the amount that you would lose is just the cost of the ticket. Now, if a person is just buying one ticket, that's just $1. Right? So what I would slip in here is, yes, the greater proportion of probability, 997 out of 1,000, but times the amount of $1. Right. So this is the modified version of the formula that we're going to use. This benefit term for the grand prize, this slightly less beneficial but still beneficial term for the consolation prizes, and then the losses overall. Let me clean up the gobbledygook and then perform the individual calculation. Okay? So, if you treat these like fractions first, it might be a little bit easier. Top times top would be 499 out of 1,000. Plus this one, 99 times 2 is what, 198? Yep. So, 198 out of 1,000. And then this loss, so minus of 997 out of 1,000. All right, remember, we add these first, and then we'll subtract from that one time. All right, so if you like, make them decimals. It might make it a little bit more intuitive, right? If you're dividing by 1,000, remember the effect. It moves your decimal place from, in theory, here to 1, 2, 3 there. So 0.499. I know that that is a little weird looking, right? Because we only have dollars and cents that go to the hundredths place. But that's what it technically would be, 0.499, right? Same thing here, divide by 1,000, so scoop this over 3 spaces. You'd have a fraction of a dollar of 198. All right, and the same thing essentially here. Dividing by 1,000 has the effect of doing this, moving decimal thrice. So minus, I put this in red, sorry, 0.997. You could do this with a decimal straight from the onset, or figure it out as you're going along. All right, anyhow, adding these, would be what? 7, 9, and let's see, 6. All right. You're going to end up getting a negative value here, looks like. Yeah. So if I got 0.697 here, and this is a negative and this is a positive, the larger magnitude will be negative when I get to this point in my calculation. I'm nonetheless going to try to figure out the magnitude brute force here, so I'm going to subtract it like so. 0, 0, and then this is be 0.3, right? Now, what is the larger magnitude? The negative, so the outcome is negative. This means that the expected value is negative 30 cents. So, in the long run, would this be to a person's advantage or disadvantage? And a disadvantage, because it's negative. All right. In theory, it's like losing 30 cents per ticket. All right, again, you did get a person who plays the game, Irene namely in this case, all right, they did get something out of it. You got 70 cents worth of experience, right? A non-monetary value, if you will. Okay. All right. Now, to answer part B, Irene's expectation if she purchased 5 tickets, can you go back and figure out intricately what each of these would be if a person had 5 tickets as opposed to 1? Yes, you can, but there's an easy way of doing this. Right? If you have already calculated the expected value of purchasing 1 ticket, then really it is just a matter of multiplying by 5. So this times 5. All right, which would be negative $1.50 in a case like that. If you were to go back and do it sort of brute force here, all right, factoring in out of 5 tickets, then you'd have to make some minor adjustments to the probabilities and to the values associated with those. Like the probability, the more tickets that you buy, in theory, the greater the probability. So what would happen is that this would become 5 out of 1,000, right? When you figure out the dollar value that would be equivalent, though, it wouldn't be subtracting 1 from 500. It would be subtracting 5 from 500, so it would be 495 for this term. The probability would be affected, and the dollar value, that the amount that is associated, that would be slightly reduced. Right? Same thing for the consolation prize, right? It would be 10 out of 1,000. there's 2 drawings on each ticket, right, for the consolation prize. And then, again, instead of subtracting 1 out of 100 to get 99, you'd have to subtract 5 from 99. So it'd be $95 in theory, right? All right. Then over here, all right, the losses, we would have to calculate 10 and 5 out of 1,000 would be the balance of, would be amount to 15 out of 1,000 would be your winning in general. So your losing in general would be subtracted from 1,000 by the amount of 15 instead. So you'd have 985 out of 1,000, right? And then minus, times $5 instead. All right. Regardless, that there's more than one way of doing the problem is what I'm getting at. But the easier way is that you take the expected value for 1 ticket and then just simply multiply by 5 tickets. And you get the same answer. Okay. One more of these, and it involves the other concept. So just to go back to this for a moment from earlier. All right, we've been calculating expected values, but now we're going to calculate fair price. So let me erase this and reiterate. All right. Expected value is essentially this formula, tweaked according to the circumstances as they are described. Fair price is the amount one should, ought to, all right, actually pay, all right, in order for something to break even in a fair game situation. Now, there are rigged games, really, right, but we're going to assume everything is fair and square, right? So what would make something fair, right? You would take your expected value, add the cost to play, right, which may be a negative or a positive, all right, and it should be a negative, of course, right? And then you will calculate what the fair price ought to be, right? Remember, break even is a situation where it is $0 net, right? Since we're talking about cost or prices, right, money is involved, and it's just as an American, I'm using dollars, okay? So with that basic formula in mind, let's say it's a 7 here. There's my bootleg paint. There it is. All right. Oh, I hate that. There we go. Sorry. All right. Expectation and fair price. All right, just to remind you, here's a formula. I hope it shows it nicely. Fair price, something that would make something fair price, is the expected value, which sometimes you have to calculate, plus the actual cost to play. But the arithmetic is fairly easy. So let's see. At a game of chance, whatever it is, the expected value is found to be, I'll put this in red, all right, negative $1.50. All right, so I'm going to put negative 0.150 here. And the cost to play is $4. Right. So I'm going to put 4.00 for the cost to play. All right, determine the fair price to play this game. All right, it's pretty straightforward, right? If you subtract $1.50 from $4, what would you get as a difference? $2.50. Right? And because we're looking for a fair price, this is what we end up with, $2.50. Right, now you might be a little leery of the sign issue here. Right, they're telling you that the cost is $1.50. Pardon me, the expected value is a negative. Right, so you don't have to look for that. Right, now you might go, well, shouldn't I put a negative here for the cost to play? Not if the expected value is already factored. Right, in theory, that worrisome part of the calculation, deciding whether something is negative or positive, is already done for you. So you don't really have to worry. So what would make this scenario fair? If the actual price would be $2.50. That means that if you did the calculation with this actual ticket value or whatever the cost to play is, all right, it would end up with an expected value of 0, right? A ticket value of $2.50 would result in a break even. Right, meaning that it would be $0 for the expected value instead of what it was. Okay, a negative $1.50. Okay, that is the last thing. So let me just give you some reminders and I'll call it quits for today. All right. Spare the bulb here. Turn that off. Lights, camera. And better benefit here. All right. Let's see. All right, for homework, if you're following the schedule, all right, do section 11.3 in my lab, and then you're in a good place. Okay. Now, just to remind you, look at the schedule here very quickly. Here's what is forthcoming, right? On Thursday, we're going to do a section 11.4, and then next week is the last week of actual new material, right? Probably going to give you this test number 3 as a freebie as well, just to free up some time, but because the final exam is going to be in my lab, I can't give you any extra time to finish up everything since, test number 2. Which is basically all of November, Chapter 9 and Chapter 11 respectively, sorry for the movement. The bottom line is, if you haven't been doing section Chapter 9 or Chapter 11 yet, you really need to do that now, because I can't give you the extra time past that Wednesday. Okay, so I'll send you a couple of reminders probably between now and then, but don't let it get ahead of you, all right? If you're following along and you're going to be working on 11.3, then you're right where you ought to be. Okay? Very good. All right. I'll see you guys on Thursday. Be careful out there.